Alright folks, so we did types of sources in the previous lecture. Now let's learn about ideal versus practical sources. Okay, and this is very basic stuff. So let's get rolling. So what is ideal source? The ideal source is a source that considers no internal resistance. So say for example you have a power supply and it rates 10 volts. Okay, that's positive terminal, that's a negative terminal, and I'm gonna call it, this is Vs. Okay, and say it is connected to some open terminals, or so say load R. The output across this load is going to be equal to what you have at the Vs, correct, which is in this case it's 10 volts. That's the concept of ideal source. So regardless of how much being current is drawn by this load resistor IR, the output voltage is always going to be equal to what is the voltage at the input, which is Vs, 10 volts. So if I would draw the the relationship between voltage, V out, and current, it's always going to be just constant. Okay, regardless of how much being current drawn, V out remains same, and again it's going to be equals to Vs, which is 10 volts. Okay, and I can write it down here. This is going to be 10 volts. Then what is practical source then? Well, whenever you hook up your circuit to power supply in labs, remember those power supply have some internal resistance. Okay, I'm gonna call it RIN. Okay, so say again you have Vs and it's rated at 10 volts, and if I connect the output terminals over here to some load, okay, RL, now this time around this output voltage over here is not going to be equal to Vs. Instead it's going to be Vs minus the current that's flowing in this circuit times Rin, which is the input resistance over here. Okay, so let's see a couple of examples over here. Okay, so say I have a circuit. Okay, here the resistance is say 10 ohms. Okay, that's the internal resistance of the source. Again, remember we are considering the practical case scenario over here. I have 10 volts power supply hooked up to this load right here, and this load has a resistance of say 990 ohms. Okay, from this we can implement Ohm's law and find out the total current, which is going to be Vs is 10 volts here, and then resistance, the total resistance, which is the sum of these two, which is 1000, correct, 1000 ohms. This is 10 volts. 0 will cancel out, so you get 0.01 amps. In other words, you get 10 milliamps. Okay, all right. So remember your V out, which is the output across these two terminals, V out is going to be equals to Vs minus I, this right here, times Rin. So if I plug in the values here, Vs being 10 volts, current being 10 milliamps, okay, and then Rin is 10 ohms, so I basically get V out equals to 9.9 volts. Now consider same circuit here. I'm just only going to take a minor change here. I'm going to increase the input resistance by two times, so it's going to be 20 ohms this time. Same power supply, 10 volt Vs. Okay, and the load over here, I'm gonna make the load value say 980 ohms. Okay, and again remember our goal would be to calculate the output voltage across these two terminals, which will be the voltage across this resistor over here. The current flowing in this circuit is just going to be calculated using the Ohm's law. So remember voltage is 10 volts, and in a series resistance of this circuit is going to be 1000 ohms, right? Again, it's a sum of these two, correct? So we get 10 over 1000, so it's equivalent to 10 milliamps. And if you notice, we had 10 milliamps over here. Okay, so even though I have changed the resistance over here, the current does not changes. Current remains same. Let's see what happens to the output, V out, the voltage across these open terminals over here. So Vs minus I times Rn. Again, we have this equation, Vs being 10, current being 10 milliamps, input resistance is now 20 ohms. So if I can do the math, I get V out equals to 9.8 volts. Okay, now notice what has happened over here. When I increase the resistance 2 times more, the voltage decreased to 9.8. When it was 10 ohms, it was 9.9, which means we would want this internal resistance in a practical source to be as small as possible, so the V out here is closest to Vs. Okay, this resistance is very tiny and it's usually in the range from 7 to 49 ohms. Okay, so that's the basic difference between ideal source and a practical source. And similarly, if you take a current source over here, okay, and you hook it up to some load over here again, okay, so this is ideal source again, your ISA 5 amps. So at the output, you also, the current flowing through this RL is also 5 amps, right? Okay, now in practical, that's not going to be the case. In practical, what's going to happen is that your current source, your equipment will have a resistance over here. Again, this is the internal resistance over here, okay, and then you have this load over here, RL. This Rn resistance, which is the internal resistance in a current source supply, is usually in the order of mega ohms. Okay, so say you have 5 amps coming in, going out of this current supply, a tiny amount of it will go through this Rn because it's a very high. Ideally you want it to be infinity, but in reality, practical, it's very high in mega ohms, and most of it will go through RL. Okay, so maybe you might have 100 milliamp going in here, and then rest of it flowing through RL in a case of a practical. So therefore the conclusion is, if we look at the voltage source, regardless of how much the current is being drawn, the voltage is going to be constant. Whereas in a practical source, because there is some internal resistance, the voltage is going to decrease as the current increases. Okay, and ideally we want this gap to be as small as possible, and therefore which would require the internal resistance to be very small. So I hope you find this video helpful, and now you have a clear sense of what's the difference between an ideal and practical source. And I thank you for watching.